Hello, this video is about kinetic theory of of ideal gas. Okay, kinetic theory related to an ideal gas. So let me get a different pen. Let's try that one there. See how that looks. Right, okay, let's talk about an ideal gas first of all. Now, an ideal gas is a gas which it doesn't matter what type of gas it is, it will behave the same. So for instance, if this is a container full of gas, it could be full of hydrogen, or it could be full of chlorine. It doesn't matter what type of gas it is. Even carbon dioxide. Okay, a larger molecule. The idea is that they'll behave the same. So here we are. These are the molecules. It doesn't matter what molecule it is. Now, what I'm doing, I'm representing. These are the molecules, like little, like marbles, or better still, ball bearings. And the next time I've drawn a vector. The length or the magnitude of the vector describes its velocity, and then you've got the direction of the vector represents its direction. So we have all these molecules moving in random directions at different speeds, and they will move along and they'll hit the sides, they'll bounce off the sides, but on average, they are a long way away from each other, so that the intermolecular forces between them are very, very weak. So what we have in here, as they're moving around, in fact, the average kinetic energy is a measurement of the temperature. But the gas itself, there's no potential energy within the gas, because there are no intermolecular forces between the molecules. And this is how an ideal gas behaves. Now, a real gas doesn't behave like that exactly, because there will be intermolecular forces between the molecules. However, as long as the pressure is not too high, and the volume isn't too small. Volume is not too small. You should find that many gases will behave in this ideal model based upon simple ball bearings bouncing around, hitting the sides, etc., etc. So let's put more detail on that. So I'm going to rub this off, and we're going to add some energy to the system. Energy to the system in terms of heat. So we're going to add heat from externally into the system. Now, in thermodynamics and thermal physics, you will find that heat is represented by the letter Q. So let's apply some heat to the system. Okay, so Q heat. What happens? Well, what's going to happen is the heat is going to go into there, and it's going to increase the internal energy. The internal energy of the system will increase. Now, there will be no increase in potential energy, because we're assuming there isn't any potential energy in an ideal gas. So all must be an increase in kinetic energy only. And the kinetic energy means that the average kinetic energy is given by the formula half mass times the velocity squared. So if the kinetic energy increases, so will the velocity of these ball bearing type things. And if these ball bearing type particles are moving faster, they're going to hit the sides not only with greater momentum, but also increasing rate, and that'll induce a force. Okay, and so you'll get a force on the sides, Okay, and if the force increases, because pressure is equal to force divided by area, you'll find that the pressure inside there will increase, and the temperature will increase as long as we have a fixed volume that doesn't increase. Now, of course, if the volume were to change, then what you'd find is that the pressure would not increase as much. So some of the energy will be used to increase the volume, and the pressure would not increase quite so much. Okay, so that's a quick idea about how gases work in the ideal model. Now let's talk about the idea of pressure in a bit more detail. What is actually happening? Now, what actually happens is to create this pressure using the idea of the kinetic theory is we'll have, this is a wall, and this is a particle going in, hitting it there, and then bouncing off and going in that direction. Now, what's going to happen is there is going to be a change in momentum, okay, as the particle hits there and bounces back again. And of course, you'll find that the force is equal to change in momentum divided by time. Okay, times. So this is the idea that there will be a force on there due to collisions, and that's what causes the pressure. Or, in fact, if it were to expand, that force will be responsible for doing work on the system, if you like, on the system on the outside. So increasing the volume, that's doing work on the surroundings.